Hi, welcome to this presentation on mantle flow distribution beneath the California margin. Much of previous work on mantle flow distribution has exploited seismological data, such as seismic tomography or shear wave splitting. In this work, we are going to examine new constraints from geodesy. At the root of the study, we assume the fact that for any plastic flow that takes place in the Earth's interior, there is an induced surface deformation that occurs by elastic coupling. So exploit this effect to infer the distribution of mantle flow from surface observations. To do so, take advantage of the Plate Boundary Observatory, which is an extensive geodetic network that includes close to 1,000 continuous GPS stations. And these have recorded at least 2.5 years of nominally interseismic deformation up to September 2018. This surface deformation, this surface velocity can be decomposed into rigid body motion and internal deformation. Rigid motion can itself be decomposed into a rotation about the origin of the coordinate system and a translation. We assume that deformation is caused by motion on faults in the brittle crust and viscoelastic flow in the ductile substrate. This is the lower crust and the asthenosphere. By decomposing the velocity field into these different types of motions, we can cast the imaging of mantle flow as a linear inverse problem. So to accomplish this, we mesh the California plate boundary margin with semi-infinite volume elements with 2 degrees of freedom. Horizontal flow can be caused by uniaxial shear in 2 different directions, 1, 1, 2, 2 components of strain rate, and also the shear component epsilon 1, 2. But assuming that the flow is incompressible and horizontal implies that the uniaxial strain components are equal and opposite. So this gives rise to only 2 degrees of freedom per volume element. We can then build a design matrix that can be inverted with the data to image the distribution of mantle flow. This design matrix is based on the effect of strain rate on surface displacements for every single volume element, the effect of fall velocity, and the effect of rigid body motion. The inversion, in fact, reduces the data very well with a variance reduction of 95% or more, and sum of square of residuals of 0.3 millimeter per year squared. So there are systematic residuals near the Cascadia Trench because the megathrust is not included in the model, and around large earthquakes due to their post-seismic effects. But these effects are overall relatively minor. So the model then provides the large-scale patterns of mantle flow, which are represented in this figure with the colors for the amplitude of the plastic strain rate tensor and the streamlines that indicate the large-scale particle motion. And we can identify several important features in these results. For example, in the central segment of the San Andreas fault, the flow is very localized and it resembles quad flow on a horizontal plane. But the terminations of the San Andreas fault system are associated with major corner flows. In addition, a large step over between the northern and southern sections of the San Andreas fault are associated with large-scale return flow that creates significant displacements, long-term displacements in the direction that's overall perpendicular to the overall axis of the plate boundary. And this has important implications for the evolution of fault activity in the Mojave section of the San Andreas fault, where the crustal faults are being advected to the east. And that explains a strange conundrum that the Ludlow fault, the easternmost fault of the Mojave section, has simultaneously the largest cumulative slip observed among all these faults, but also the currently slowest rate of slip accumulation. In addition, this kind of perpendicular motion of mantle flow advects the Garlock fault to the southeast, and that also explains the emergent activity of the White Wolf fault. We can also think of the recent 2019 Ridgecrest earthquake as a prolongation of seismic activity on the White Wolf fault. And together, these faults may supplant the role of the Garlock fault in the triple junction between the central segment and the big bend of the San Andreas fault. Understanding mantle flow is important to understand stress accumulation in the crust, because strain rate in the ductile layer is aligned with the deviatoric stress, and also the stress is simply the integral of the stress rate, and the stress rate is aligned with the strain rate. And so this is confirmed by several observations. For example, here you can see that the orientation of strike slip faults, which are shown in red in this figure, are aligned with the direction of maximum shear of plastic strain rate, shown by these double vectors. So strike slip faults are aligned with the direction of maximum shear. Major thrust faults are aligned perpendicular to the direction of maximum compression. And we can also compare the direction of plastic strain rate with the compressional axis of seismicity clusters, here shown with these bars. You can see that there is an overall agreement between seismic focal mechanisms with the direction of plastic strain rate. So that indicates that there's a strong mechanical coupling between flow in the ductile layers, the asthenosphere, lower crust, and stress in the brittle crust that controls then the orientation of faults themselves and the focal mechanisms of earthquakes. Plastic strain rate also shows a strong agreement with the orientation of seismic anisotropy in the Mojave mantle. Seismic anisotropy can develop with lattice preferred orientation, which accrues with plastic strain. So the plastic strain rate provides some indication about the orientation of plastic strain. However, a more accurate model must incorporate how the plastic strain rate evolves throughout streamlines. In addition, the plastic strain rate creates plastic anisotropy and seismic anisotropy in the directions of maximum extension or the direction of maximum shear, which differ by plus or minus 45 degrees. So given these uncertainties, there is a good agreement between the direction of seismic anisotropy and the direction of the principal direction of plastic strain rate. So we can continue exploring the relationship between mantle flow and crustal deformation by comparing the long-term slip rates on major faults with the integrated strain rates immediately underneath in the mantle. And these two quantities show a good agreement for faults with fast slip motion, but less so at lower slip rates and for faults that are in an extensional environment. Nevertheless, this is also a strong indication that there is significant interactions and mechanical coupling between mantle flow and crustal deformation. Finally, I'd like to show how mantle flow compares to plate motion at longer time scales. To do so, I compare the integration of plastic strain rate in a direction that is perpendicular to the overall axis of the plate boundary. And I compare this with the relative long-term plate motion between the North American and Pacific plates from magnetic anomalies. And you can see that the integration of plastic strain rate agrees with the mean and standard deviation of different estimates of plate motion over long time scales. This map also shows that there is a strong spatial correlation between the distribution of seismicity, small and large earthquakes in California, in regions that currently experience intense plastic strain accumulation. So once again, we see a strong connection between mantle flow crustal dynamics that manifests itself by intense seismicity in regions of strain accumulation. So to conclude, we provided an image of the mantle flow patterns along the California margin that indicates how the plates move past each other at mantle depth. And these results indicate strong mechanical coupling between the mantle and the crust at different time scales, and an agreement between the current plastic strain accumulation in the mantle with the long-term relative plate motion at geological timescales, with also an agreement between the current plastic strain rate orientation with the orientation of strike slip and thrust faults in the crust and the orientation of earthquake focal mechanisms. We also notice that faults just closely pack around region of large strain accumulation. So we can imagine that the deformation is accommodated by slip partitioning in the crust, but strain partitioning in the ductile substrate with geographic overlap.